Good afternoon. So I want to start talking about matrix representations. Okay. So the basic idea is like so far what we have been doing is we write down like a partial differential equation, right? PDE, which was like Schrödinger equation. And we solve it and we look at the solutions and we use the rules of quantum mechanics, right? And we do this so-called Copenhagen interpretation. It's like wave function is the probability, right? The square of wave function is the probability. And if you make a measurement, wave function collapses to that state, and so on and so forth. So it's like if you want calculus-based approach to quantum mechanics. So this is like so-called wave mechanics, and this is due to Schrödinger. But in parallel to this wave mechanics, there was also a linear algebra approach to quantum mechanics. And that's what we call matrix mechanics. And that's due to Schrödinger, Heisenberg. I think in the 1920s, people were not sure about how these two approaches were like reconciling with each other. But later, I think mostly due to Paul Dirac, today we know this is identical description, right? Wave mechanics and matrix mechanics are exactly the same thing. And now I want to spend a few lectures to do everything we did in terms of matrices. And that's why I call it matrix representations. Good. So the basic idea is we have a differential equation. Plus some other conditions based on physics, like normalizability and boundary conditions. And boundary conditions is also related to normalizability. And if you impose all of these things, what you do is like you find a set of functions which yields a set of functions. And these functions are kind of like vectors, kind of like this three-dimensional vector we are familiar, like x, y, z in the Cartesian coordinates. But the space is not a vector, it's not a vector space, but it's like a different kind of vector space. That space is what we show with H is Hilbert space. And these functions that comes out of this solution of differential equation are like, let me call it B, which is something like, I don't know, you can think about particle in a box, harmonic oscillator, or like, I don't know, spherical harmonics. All of these are, this is B, basis. Okay, I cannot, let me write it like this, B. There's like a set of functions, phi1, phi2, dot, dot, dot. Generally infinite dimensional, but sometimes it can also be a finite dimensional. So this is a basis. Therefore, any function in the Hilbert space, so let me write it like this, phi, because this is like a basis vector, right? Take any vector, you can decompose this vector to its Cartesian components, right? If this is V, it has like an X component, Y component, and Z component. Similarly, any vector in the Hilbert space can be decomposed to it's like basis vectors. And I want to write it like something like this. This is n, some expansion coefficient Cn, phi n. Good. So some examples. For example, for particle in a box, this phi n becomes these sines and cosines, but because of boundary conditions, we only have sines. I think 2 over a sine n pi over ax. You can think about 1D harmonic oscillator. Then this phi n becomes these Hermite polynomials. Let me write okay, let me not write it. It's like some normalization constant an times hn of xi, and this xi, okay, this is a function of x, and xi is m omega over h bar times x. And we didn't do these this semester, but they are from like 300. But this semester we did, for example, these spherical harmonics, phi. For example, for the free particle in 3 dimension in spherical coordinates, we had like this k, l, m's, and they were up to normalization, some j, l, k, r, y, l, m, theta, and phi. These are complete set of functions that can describe any function in the Hilbert space. Or lastly, hydrogen atom. And for those phi, we had 3 quantum numbers, n, l, m, and up to normalization it had like some radial part which was written in terms of Laguerre polynomials, and l of r, and there was also this spherical harmonics, l, m, theta, and phi. Good. Yes?
Should the summation be finite?
Should the summation be
Finite.
So this summation,
Yes, that's
I mean, if like some problems, for example, we'll come to spin. Spin is like a 2-dimensional Hilbert space. It's finite. But in, for example, particle in a box, the Hilbert space is infinite dimensional, right?
I'm not asking for the basis set, but for the summation. I know the basis sets.
So this summation, right?
Should it?
Any basis, any function in the basis can contribute to state in the Hilbert space. Of course, for example, if you are close to ground state, it's going to be a finite number of basis states contribute, right? But in general, this sum is, I think, it can be infinite, especially at a high energy state. If you want to describe a high energy state, you need to have like many terms in the sum. But typically, I'll show you like some practical examples. Even if the Hilbert space is infinite dimensional, you put a cutoff, right? You put a cutoff and you work with finite dimensional matrices. So okay, so what we do is like we have like an abstract state, which is an element of Hilbert space, and this abstract these basis functions are complete in the sense that if you do this, let me use this for wave function. This is like completeness relation, and you can put, so this is like a fed one. You can put this one anywhere you want, and I am going to put it here. So this is going to be psi is equal to sum over n psi, and this is what we call the expansion coefficient. Let me call it Cn. And any abstract vector in the Hilbert space can be written in terms of these basis vectors. And here I am using like n for this phi of n. And this phi of n can be like particle in a box, 1D harmonic oscillator, or any other problem. So this is the meaning of this is like these expansion coefficients are projections of state, right? This is the projection of the state onto basis vectors. Therefore, so what does this say? For every state in the Hilbert space, let me write it like this. There is like a set of coefficients, like Cn, right? Typically infinitely many states, but it can also be finite. And these set of coefficients are representing this abstract state in the Hilbert space. Okay. If you want, what we are saying is like this set of coefficients are equivalent to state psi. That's what I mean. These coefficients are representing the state in the given basis. And so these are the states, but we also have operators like momentum and position, right? Like an operator hits on a state and gives us another state. Let me call it phi. Let me write it phi prime to know which one's after the action. And I can do exactly what I did. So I can put here this identity and this is going to be psi prime. And now I can take the projection of both sides on a state M, like multiply, if you want left multiply M, and then what we'll find is, let me do it in 2 steps. So I'll do this M, and from here I'll have M, and this coefficient I'm going to call it C M prime, and here on this side what I have is sum over n f m n c n, and this f m n is defined as, so this thing is defined as f m n m f n, and this thing you can see is, what is this equation? Anyone with any student of linear algebra recognize that? This is like a row vector multiplying a matrix, right? So this is matrix f m n multiply row vector Cn, and it is giving us another row vector Cm prime. So this is like a matrix vector multiplication. So this thing is actually, let me also elaborate a little bit. So this may still look abstract to you, but you can think of f to be like a position, for example, and this is going to be in the basis, I don't know, some dx phi m star of x f phi n of x. Good. So you go from these functions, continuous functions, to matrices and row vectors. Yes.
M is in the sigma and or in the right side is not different, right? I mean numerically.
M
and M prime is not different.
They are different, right? So in general, you have like M, like this is like a matrix, right? So this is, if you want, in this case, F is represented by F11, F12, F13, dot, 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 F1, F21, dot, 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 F31, dot, 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 and so on. I'll show you some examples. They are generally, they can be equal, but they can also be unequal, m and n. Right? The most general operator has all these matrix elements. And like Cn here is like represented by, I don't know, C1, C2, dot, dot, dot. And Cn prime is represented by C1 prime, C2 prime, dot, dot, dot. We continue. Like suppose an operator is given like some g and acting on some basis function phi n, and it is giving us, I don't know, some gn phi n. So this is what we call eigenvalue equation in this abstract form. And the basis is again like this phi 1, phi 2, dot, dot, dot. And if you want to look at the matrix representation of this operator G, we can take product with phi m from both sides. Phi m G phi n is equal to, so this Gn is just a number, right? Numbers just go through everything else. So this is Gn, this is phi m phi n. But these are like orthonormal vectors, just like basis vectors in the Cartesian coordinates. So this is delta m n. Therefore, this g m n is equal to gn times delta m n, which is a diagonal matrix. Therefore, in the basis where this eigenvalue equation is satisfied, the operator is going to be diagonal. And you can also think about representation of states, like a representation of, for example, phi n. I can put 1 here. So this is going to be m phi, okay, this is m phi m phi m phi n, and this is delta mn. Therefore, the coefficient, right, which is the coefficient of expansion Cm, Cm in this case is represented, but with 0, 0, dot, 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 there is 1 in some empty place, and all the others are 0. Yes, Hermitian, okay, just a quick reminder from like 300s. Observables are represented with Hermitian operators, right? And Hermitian operators have real eigenvalues, and because these eigenvalues correspond to observations, right? And observations better be real. And any Hermitian operator, if you diagonalize it, its eigenvectors are complete. That means any other vector can be written in terms of eigenvectors of Hermitian operators.
But then aren't they just like automatically diagonalized?
Aren't they
automatically diagonalized?
If you are in the basis of that Hermitian operator, they can be diagonal, yes. But I can be in a different basis. Even though it is like a Hermitian operator, it doesn't have to be diagonal. It may have off-diagonal elements and still be Hermitian.
But how do we saw that this in the G case with the eigenvalue function that the capital G is
yes.
his own basis?
So I think I'll come to Hermitian conjugation just in a little bit. You'll see, right? Any matrix can be Hermitian conjugate, right? And still can have off-diagonal elements. Just in just one moment. So let me also remind a little bit from 300. So if you have like A, B, C, these are operators, but I'm not going to put head. If you want, I can put if you feel better. So these are complete set of commuting operators. And in this case, the basis B, phi 1, phi 2, dot 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 are going to be simultaneous eigenstates of all of these operators, right? And an example to this is A can be, for example, H, Hamiltonian of Schrödinger equation, for example. B can be L squared, and C can be LZ. And eigenvectors are labeled with the labels of each operator. For example, this one is N, this one is L, and this one is M. And basis vectors are going to be indexed by this N, L, M quantum numbers. Good.
What exactly do you mean by complete?
Like complete in the sense that you cannot, right? Like I think last week we argued that it is a little bit trial and error kind of approach. Complete in the sense that for a given problem you cannot put any other operator in this set that commutes with all the others. But you know, physicists, we don't prove anything, right? I mean, complete in the sense H, L squared, and LZ, they commute with each other, and there is no other operator you can. Actually, there is. For example, there is one more operator you can put this in this set, and it's called Runge-Lenz vector, and that actually explains why spectrum of hydrogens degenerate. But even if you don't know that, right? Even if you don't know that, we say that this is the complete set, and that's it. Yes.
We also say that we can form any operator with combinations of these operators.
Yes. Not like that, right? I don't think you can form any. For example, I can give you an example. Lx, you cannot decompose Lx in terms of these operators. But Lx is still represented in this Hilbert space. I'll show you in a little bit. So there can be other vectors which are not expressed in terms of this set. But the key is, this is the biggest set with the property that everybody commutes with everybody else. And the more operators you can put in that set, the better resolution you have about your Hilbert space. Good. So let me also mention the continuum case. So these are like all discrete, but in the case of continuum problems, for example, free particle in 1D. So in 300, what we said is like Griffiths calls this the suburbs of the Hilbert space. Technically, they are not in the Hilbert space, right? Because they are not normalizable and all these things, that they don't exist. But you can define a generalized normalization, so-called Dirac normalization, and you can do all of these things we are doing. So, and typically they have like continuum spectrum, and you can also look at, for example, matrix elements, K prime. Let's look at the Hamiltonian's matrix elements. So this is going to be K P squared over 2M K, and P squared acting on H. Okay, this is K prime. So this is going to be H bar squared K prime squared over 2M, and K prime inner product with K is going to give us delta K prime. And if you sum over K prime, K, H, K prime, you can, in the continuum case, these discrete summations, they go to integrals. We have dk from minus infinity to plus infinity, and H bar squared K squared over 2M delta of K minus K prime, which is H bar squared K squared over K prime squared over 2M. And for example, it doesn't have to be momentum. You can also think about position operator. For example, let's consider 1D harmonic oscillator with the Hamiltonian, which is given by minus h bar squared over 2m d squared dx squared plus 1/2 m omega squared x squared. And we have h psi, e psi. So this is the real space representation. We can go to momentum space. In the momentum space, right, we have e to the I kx. If you take the derivative, you have ik coming in one time. If you take second derivative one more time, what you are going to have is h bar squared k squared over 2m sum b of k plus 1/2 m omega squared del squared over del k squared. So this is x square operator in the momentum space acting on this expansion coefficient is equal to e times b of k. So I think this is, let me write it this form. So this is I del squared. So again, if you want to know more about this, I think we spent quite a bit of time in 300. You can either read Griffiths or go to our lecture notes. I think if you feel uneasy, it's there. So now I want to give you a couple of matrix relations which are going to be useful. Let me summarize. Also, Griffith's appendix is like a good source if you have any difficulty with linear algebra. I think it's very elementary, and if you want a refresher, go read it. It's 1 or 2 hours of read. For example, we can have two matrices A and B, right? A times B is a matrix, and I can look at I and jth element of this matrix. And what we write is, we have some K, A, I, K, B, K, J. And if you use the summation convention, right, repeated indices are summed over, we can write this as K, B, K, J. So this is summation convention. And we can think about inner product between two vectors in the Hilbert space, psi prime and psi. And we can put this fet 1 here, and it's going to be n psi prime and psi, and this thing is Cn prime, this thing is Cn, and this we can think about this operation as a row vector times a column vector, like this is C1 prime, C2 prime, dot dot dot, multiplying C1, C2, dot dot dot. Yes, yes, you are right. Let me. So this is star. I think. Thank you. So inverse of an operator is defined by, so inverse a to the minus 1 times a is equal to a to the minus 1 is equal to this 1. Transpose a transpose mn is equal to a and m. You just swap the indices, and we call a matrix symmetric if symmetric if A is equal to A transpose, and anti-symmetric if A is equal to minus A transpose. So trace of a matrix is shown with this trace A, and it is defined by sum over all n, n, a, n, which is sum over all n, a, n, n. And Hermitian conjugate, okay, that's your question. We show it with a dagger, and this is equal to a star transpose. We take the transpose and the complex conjugation. Sometimes some resources call this Hermitian adjoint. There's the same thing for us. And for example, I can look at this. A dagger mn is equal to a n m complex conjugate. Like, look at the matrix in nm index and just take the complex conjugate. And I want to remind you, like, Hermitian conjugate in the most general case is defined like, if you have phi n phi m a phi n. So you can take any operator and choose to operate it in the bra space. And the form in the bra space is Hermitian conjugate. So this is equal to a dagger phi m phi n. Right? This is acting in the bra space. And one more thing, like, matrix is unitary, like unitary, if Hermitian conjugate is equal to inverse. Therefore, for a Hermitian, for a unitary matrix, U dagger U is equal to U dagger is equal to unity. Good. Maybe I can give you an exercise and take a break. So exercise. Show that eigenvalues of a unitary matrix have unit norm, like lambda is equal to 1. Good. Let me also introduce something called unitary and similarity transformations. So let's think about like a familiar Cartesian coordinates. We have, I don't know, some axes, and in this axis I have a vector v. You want, this is y, this is x, and this v has v is equal to vx vy. But this x and y is our choosing, right? I can choose these vectors, and maybe you are like, I don't know, in a different orientation, and your axes can be a little bit different from mine. For example, we can have, let me try to rotate this piece. Okay, maybe I can do that. Okay. So what I'm trying to show is like the red vector is exactly the same, but I can rotate the axes. Let me try to do it like this. It's a little bit harder to draw here. right? So this is, if you want x prime, this is y prime, and this vector v, even though it is exactly the same vector, its components are different. That's why I want to put like a prime here, the x prime and vy prime. If you want, this is like a rotation around z-axis by angle phi. So this is rotation by phi around the z-axis. So what this rotation does is, like, for example, the inner product, right, v dot v, which is the length of the vector, is equal to v prime dot v prime. So this is the same length. So the length after this transformation is preserved. But also I can look at two different vectors. Like this is like a red, and I can think about, I don't know, another one like this is v2, and I can look at the inner product between v1 and v2 in the first coordinate, and we know, right, it is because their length does not change. The angle between them do not change with the coordinate transformation. Therefore, this angle should also be preserved with this transformation. And I will put primes here. So this is like a one particular transformation. In general, transformation from one basis B to another in the another, let's call it, I don't know, B prime in the Hilbert space is called unitary transformation. For example, we can think about phi n. Let me just write this slope notation, and I can transform to another, I don't know, phi n prime. And these are two different bases. Then phi n prime, I can expand it in terms of this original basis. Right? I can put this phi n. Let me use another index here, m. So this is m. So this is m. So this is prime n. And this, you can see this is like a two-index object. It is like a matrix, and I'm going to call this U, N, M complex conjugate. Therefore, this U, N, M is going to be defined by phi n prime, phi m. So this is like a projection of new basis onto the old basis. Like let's think about a state in the Hilbert space like psi, and we know this state is going to be represented with some psi n prime coefficients, which is defined by projection of this state on my basis vectors. Like let me call them phi n prime psi. And I want to look at this phi n prime. In the bra version, it's going to be equal to, again, I'll put the unity m phi m phi what am I doing? I'm trying to do phi m phi m phi n prime. And this is exactly sum over all m u n m phi m. Now I want to look at this object, right? I want to look at this phi n prime, psi n prime. Psi n prime is equal to, I'll just plug this result into here, and this is going to be sum over m u n m phi m psi. But this is the expansion coefficient in the original basis, which I'll call it psi m, and I can write this as sum over all m u n m psi m. And what we see here is like this operation. And what is this? This is exactly psi prime is equal to u psi. So has above matrix representation. Good. Okay, this is, if you want, operator form, and this is the matrix form. Let's also, okay, so this is how I transform in the Hilbert space. This is exactly like this rotation, but we operate with these matrices, right? Unitary operators. And we can now also consider the inner product. Let's consider two states. Psi and phi, and psi prime with this, right? This is psi prime is equal to u times psi, and phi prime is equal to u times phi. And I want to look at the inner product. Phi prime in the transform basis, it's like phi prime psi prime is equal to, I can use this. This is phi, and when I take it in the bra, this is going to be u dagger, and this thing is u, and this thing is psi, but u dagger u is 1, therefore this is phi psi. And this is how unitary transformations preserve length and also angle between states in the Hilbert space. Good. Let me also think about operators. So what we said is like f acts on a state and it gives us another state psi. So this is like a typical equation in the Hilbert space. And I want to write, right, so this thing, so this, let's take this and multiply both sides with u minus 1, u to the minus 1. u minus 1 is 1, so I'm going to write it like this. And similarly, psi is equal to u to the minus 1, this one, times psi prime. Now I'm going to put this in that equation, so let's write this equation. And on this side I have this, and on the other side, like, let me push it like this, I have this. And now I can multiply both sides with u. So this is u times u to minus 1 is 1, right? And before the transformation I have this equation, right? After the transformation I have this equation, and from comparing these two I can conclude how this unitary transformation changes the operator. So this f will go to u f u to the minus 1 is the I think the book sometimes call it unitary similarity transformation, but I think physicists generally just call it unitary transformation. So this is unitary transformation of operators. So for states, we only act with u, right? For the operators, we have u and u minus 1, multiplying the operator from right and left respectively. Good. Any questions? Okay, these are like summary of linear algebra that we are going to be needing in the following weeks. Let me give you some exercises, and I will give you some examples of these matrix representations. Exercise. So show if A is Hermitian, it stays Hermitian under unitary. So just use this and take the cohermitian conjugate, and you are going to see how this works out. So more importantly, show eigenvalues of Hermitian operator do not change with unitary transformations. And more importantly, show determinant and trace do not change with unitary transformations. Good. Let me close this, and I want to start like a next chapter, which is going to be basically examples of these matrix representations.